Yeah, also hello from my side. I'm happy to announce Tobias as a speaker for our seminar today. Tobias is here since summer on a tenure track professorship for machine learning, but he did his degrees in automatic control and in robotics at ETH. So he comes from like a background that is quite broad. And since then he worked as a postdoctoral researcher at EPFL Lausanne, from which we were able to grab him. And we are really happy to have this kind of addition to our Fachbereich. And what is really interesting about Tobias is that he works not just in pure machine learning, like throwing problems to whatever, a big network and then looking what is going on, but he's interested in the problems that are like around it, like combining optimization and machine learning, or even writing some papers about quantum computing. And what I found really nice, and that I just realized a minute ago, that he has like a twin brother who works in physics and who is like coming from the physics side and you're coming from the computer science side, and together they write papers about like quantum speed-ups for example, dynamic programming and other problems, because as he just mentioned to me, it's still so rare that you find real good algorithms for quantum computers that are exponentially faster than classical problems. Yeah? So you see, like Tobias has like a broad range of interests and things, and we are very much looking forward not just to the talk but also to the works you will do here in Constance. So the stage is yours. Thanks.
Thank you so much, Oliver. Thanks to everyone for giving me the opportunity to speak here. So let me start sharing my screen and start the presentation. Yeah. So as I said, like I'm very honored to be given the opportunity to speak here in front of this fantastic collective behavior colloquium. And as Oliver also already mentioned, I'm relatively new here, and therefore I thought it's a good opportunity to introduce my research interests to a bigger community, and therefore I also decided to give rather a broad and maybe sometimes a little bit a high-level presentation spanning different aspects of my research interests, and also I try to a little bit adapt my presentation to problems that could potentially be interesting to people working on collective behavior. So yeah, the hope is that after this presentation you know better what I do, and of course I'm very much looking forward if anybody would be interested to contact me after this presentation, and we could have a discussion after that. Good. So with that I would like to start with the first slide, which is a quite high level one. Just a little bit covering like my research interests, that you get a little bit an idea who is here and what I'm interested in. So the first block, which is my key interest, is data science or machine learning. And of course these problems are highly motivated by several applications in the domain of artificial intelligence. So that is the kind of key block. But then, as Oliver also said, like I have a keen interest in the more algorithmic domain of mathematical optimization problems, and how you actually provably solve the underlying mathematical optimization problems and developing algorithms there. And this, of course, is closely connected to a discipline known as operations research, where you analyze complex networks and complex systems and give more emphasis on the underlying optimization problems. And the last block, I would say, is that of optimal control. So this is a rather, I would say, traditional discipline where you have this type of dynamical systems, and your goal is to optimally interact with the dynamical system with the goal to steer the dynamical system to a certain target state. And yeah, while this is a rather classical discipline, now with the rise of data-driven methods and machine learning, you will see, and this is also one of the goals of my presentation today, that this is actually very, very closely interacted or aligned to what is called today a reinforcement learning problem, which is a key block of machine learning these days. So therefore, like these three disciplines, while looking a little bit disjoint at first, are actually very, very much connected to each other. Good. So then, yes, let me try to do that. It's a good point. Maybe to the very bottom. Good. Thanks a lot. Okay. So I thought what would be a good kind of anchor to ground my presentation? And I decided that a good thing is a very classical optimal control problem. And even if you have not heard of an optimal control problem, it's quite simple to understand, I guess. So the goal of an optimal control problem is that you want to find the best action, which is the symbol AT. So you're optimizing over the set of all potential inputs or actions to your system AT, and at each time step. Now the goal is to find an action sequence AT such that a certain cost function is minimized. Or sometimes people also speak about maximizing a reward. Machine learners like to maximize rewards, control people like to minimize costs, but those are actually the same things. So let's stick with costs for the main part of this talk. And so we're trying to find like a sequence AT such that on expectation this cost here is minimized. And we have the little c, that's a function known as the running cost that depends on two arguments. The first is the state, the position of your system at time t, and the second argument, the AT, is what we optimize over the action, the input that we apply to the system at time t. And then, okay, there is this terminal cost here, which is just affecting the state at the terminal time t. So this is not so important. We could also assume this to be 0 for this presentation. And then now what is the difficult part in an optimal control problem is that you have an underlying dynamical system. And this is also what I think differentiates that then from classical machine learning problems where you just want to do classification or regression problems. So here really you have an underlying dynamical system that is represented as this difference equation. So the state is updated according to time, according to this dynamical system f theta. And okay, I decided for simplicity to go with a discrete time system, but you could of course also think of a continuous time system, an ODE or stochastic differential equation that could, like model a physical phenomena. Good. So now, so why should I present this optimal control problem? So one idea is, or one motivation is that these problems appear in various application areas, and I listed a few here, and the list is much, much larger. So I don't want to go over all of those in detail, maybe start with the first one to explain a little bit how we would actually phrase an autonomous driving car as an optimal control problem. We would have the state, and a very simplified setting would be the state is the position of the car and the velocity, right? And then you would derive like the Newton law of motion, which is an ODE, can be time discretized, so you get this dynamical system. It's just a Newton law of motion, and what would be the input? The input would be the acceleration that we as a driver insert to the car, right? To the autonomous car. Now, what would be the kind of cost function? So the cost that depends on the problem we are interested, but for example, you could say we want to go from A to B in the minimum amount of time while using as little as possible energy. And that could be directly phrased as such an optimal control problem. And it's actually also what is used, right, in many of these kind of robotics or autonomous driving models. Now there is other more data-driven approaches where you have online marketing. You want to maximize the reward of sales as an online retailer, and the decision or the action AT is which ad to show to which person at which time, and so on. So the third one could be building control. You want to control the temperature of a huge complex building complex, such as the University of Constance. And of course, the input AT is which radiator in which building should insert how much heat or energy to the system. And S of T would be the temperature in each building. And of course, this is a dynamical system, right? So there's the heat equation that describes how the temperature evolves over time, and this is affected by the temperature in the building at time t, also how much energy you insert to the system, and the external noise, which could be the sun hitting the windows and this type of parameters. Good. And this list goes on, and biology, robotics, etc. But I mean, this is not my point to go over this list, but rather to convince you that such an optimal control problem is actually quite a rich modeling framework of physical and natural science problems. Good. So now, with this optimal control problem introduced, I can give an outline of the presentation that I would tell you today. So we have now the optimal control problem, and this is characterized by the cost functions, the dynamical system, and the exogenous noise. And now, depending on which of these three parameters are known and which are unknown, these problems have slightly different names over the last decades. So the most classical one is when everything is known. So your cost functions are known, your dynamical system is known, and your noise is known. Then this is just a classical optimal control problem, and it's known since the years of Richard Bellman how to solve this, namely by dynamic programming. And I would just like to point out that even though algorithms exist to solve these problems, these are computationally very difficult problems. So they scale exponentially in the dimension of the state and action space, which is known as the so-called Bellman curse of dimensionality. So just to make clear to everyone that even in the simple case where everything is known, these problems are notoriously difficult. Now, of course, in many applications, for example, the underlying dynamical system is unknown. You don't know the dynamical system. But you have maybe data from historical trajectories and observations. And then, okay, one could ask the question, how could we solve this optimal control problem with using data instead of the model? And of course, okay, machine learners have thought of that a long time ago, and they coined this problem the so-called reinforcement learning problem. So you can really think of a reinforcement learning problem as an optimal control problem where the underlying dynamical system is unknown. And this is a problem I would like to talk about today. So here, hidden under this Zoom thing, is the focus of today. Yeah? And then one could go even further and say, not only is the dynamical system unknown, but also the cost function is unknown. So I observe, let's say, expert trajectories or behaviors, and I would like to understand or to infer which cost function or which utility function was actually maximized by the underlying agent. And this is then known as a so-called inverse reinforcement learning problem. And for this problem, I would also like to maybe touch that at the very end of my presentation. I think there is huge kind of motivation and applications for that in understanding collective behavior and understanding why animals or humans behave the way we see. Good. So that will be the link to the cluster here. Okay. So with that, I would like to get started with an introduction to reinforcement learning. And here is, okay, the last kind of marketing slide. So we have seen in the last decade, I would say, a tremendous progress when using data instead of models, right? When replacing the underlying physical model with a purely data-driven approach. And this has led to this impressive series of works, mainly driven by Google's DeepMind, where they could, for example, design a computer program that could teach itself how to play chess better than the existing world champion, just purely based on a data-driven approach. Now, motivated by this hugely impressive success, questions arise like, why do these methods work so well, and actually could these methods be generalized to other problems, such as a self-driving car or an optimal building control problem. And this is where current research is a little bit stuck. So it's not clear a priori when and why these methods showcase such an impressive performance. And this motivates much of the theoretical research in this problem. So one would really like to understand when and why do these methods work, and even more interesting, when do they not work? Okay. So this is the motivation why fundamental research on that questions is heavily needed. Now, putting the machine learning hat on for a second, so we have seen now the reinforcement learning problem as an instance of an optimal control problem, but there is a slightly different approach to a reinforcement learning problem via the machine learning hat, where you say, okay, machine learning problems very roughly can be grouped into three main classes. One is a supervised learning problem, where you have, labeled data, and you want to classify or you want to predict the value of new data that everybody knows. The other one is unsupervised learning, where you have basically clustering problems. You want to group data and find patterns in data. And the last block is a so-called reinforcement learning problems, where you interact with the system. So this is something that you adaptively learn by interacting with the system. And now, if you would open a reinforcement learning textbook, you would find this as an explanation of what is a reinforcement learning problem. And actually, we will see that this is nothing else than an optimal control problem. So a reinforcement learning problem consists of a decision maker, that is the person selecting the action AT, and it has the environment. So the environment, in the past I called this the dynamical system F theta. And now, so what does the decision maker do? The decision maker has access to the current state S at time t, And then the decision maker, she selects the action A at time t with the goal to minimize costs, or here to maximize rewards. That's exactly the same thing. And what is the difficulty in this problem? The key difficulty is that I already touched it before, that is a sequential problem. So selecting an action at time t not only affects the current reward collected at time t, but it steers the state to a part of the state space. And therefore, you will potentially suffer higher costs or lower rewards in the long term by selecting an action. So you cannot just do a greedy kind of optimization of the actions. You need to do a sequential optimization over all actions. And this is what makes this problem so much complicated and actually also so much interesting. And the second difficulty, as already mentioned, is that the environment is unknown. You don't know the environment in reinforcement learning. And therefore, like very kind of high level, the decision maker is always in conflict with two things. So either she could play an action with the goal to learn more about the unknown system, with the goal that later, once you know the system better, you can control it better and maximize the rewards. Or you could say, okay, I'm at the moment t trying to find an action that gives me a low cost or high reward, and I don't care about learning the environment. And this kind of dilemma, or this kind of tension between learning about the unknown system and minimizing the costs, is known as the exploitation dilemma, and it can be also understood in a very practical meaning. So imagine that this gentleman here has figured out many restaurants in Constance, and so he knows one restaurant which is his favorite place, the usual place. He knows that on average food quality there is really good, and he's very happy about it. And now imagine that there is a new restaurant opening next to it. Now this agent is now challenged with, okay, should he try out a new restaurant with the possibility that food there is even better, but there is also the possibility that food there will be awful, which will be a very high cost or a very low reward then. And so therefore now it's not clear a priori whether the agent should now explore, go to the new restaurant, or exploit, meaning go to the usual place. And of course, this was just a two-situation scenario. Like in general, like there is infinitely many possibilities to check out. And therefore, this exploitation dilemma in general is very, very hard to capture. It is one of the key difficulties of reinforcement learning problems. Good. So now, the second part. So this was more the statistical point, how much should you explore, how much should you exploit. There is also the kind of algorithmic approach, the optimization approach. So these problems rely on a mathematical optimization problem. And mathematical optimization problems are particularly hard when you have uncertainty in the optimization problem. And the optimal decisions of optimization problems can be very sensitive to uncertainty. And I try to give that to you in the following example. So think of a very simple example. You would like to travel from home to the University of Constance. You have n different routes you could take. Each route has different traffic and different kind of weather condition, which is uncertain, so you don't know. But your goal is to minimize the travel time. So you could write it down as the following deterministic optimization problem. You want to find the route such that the travel time L is minimized. And the travel time L depends on which route you take, of course, but then also on the external parameters, the traffic along these routes, the weather, etc., right? And you don't know this, so this is an uncertain parameter. Now, since you don't know these parameters, how would you solve this optimization problem? Because it's modeled as a random variable. Now, a naive approach, or a first idea would be, how do I put this? A first idea would be to just replace this uncertain parameter with its mean and think, oh yeah, mean is a good approximation of a random variable, so let's just then solve this minimization problem where the psi is replaced with its expectation. And you would hope that maybe this doesn't give such a bad approximation. Now, it turns out that this is actually, this can lead to very bad decisions. So this can have very fatal consequences, and it's best illustrated with a very famous cartoon. So imagine this gentleman that was in the pub and is now drunk on his way back home, and now so the position or the position of this gentleman constitutes a random walk, and now if you assess the health or the security of this gentleman based on the mean position, you would be led to believe that he's in perfect health, right? Because the mean position is just the middle line of this busy road, and that is a safe region. However, the average state of this gentleman is drunk, because he will never be exactly on the middle road. That is a probability zero event. And therefore now assessing the quality of this situation based on replacing the position by its mean leads to a very fatal misjudgment of the situation. So already by this simple cartoon, it can be well understood that replacing uncertain variables with its mean is not a good idea in general. So what then is a good idea? A good idea is to consider a more kind of realistic or more sensitive model for uncertainty. And that is that of a so-called risk-aware model. So when you want to minimize the travel time, you not just replace the uncertain variable with its mean, you minimize the so-called risk measure of the travel time, or little l is the loss function. And there is different notions of what could be a good risk measure or a good measure of the risk. The simplest one, and that is the one that we will discuss today, is just the expectation. So that we say, okay, we want now to find the route that leads to the smallest travel time on average. And if we take this route, or if we do that every day, right, by the law of large numbers, we will see that this is not so bad of an approximation of what we do. Now, there is other risk measures. So one could also say, I want to find the route that leads to the smallest travel time when I consider the worst case realization of all noise and traffic parameters, right? That is the second risk measure here. That is kind of a worst case consideration. And this is what people use a lot in game theory. That is a very conservative one, but sometimes a good one to consider. And there is other risk measures in between, like a value at risk, conditional value at risk. I don't have time to go into all of those. I would like to stick on the first one, because this has a nice connection to machine learning. So now, we are looking at minimizing or finding a decision X such that the expected loss is minimized. And of course, for anybody having seen like statistical learning problems or machine learning problems, that is the key problem that machine learning is interested with, right? They try to find a hyperparameter X such that the expected loss is minimized. And what is usually the difficulty is that the probability distribution of Xi, the P, is not known, but it has to be learned from data. Good. So that, so far so good. There exist many tools for that. And then in the second step, when we say, okay, we learned this P from data, and we can somehow, like approximately evaluate this expected loss, there is still the optimization problem. We still need to solve the minimization over X. And that is not a priori clear what is the computational cost of doing that, or whether we can even hope for solving this problem, polynomial time. That is what I mean by a tractable way of finding the X. And then last, we are ultimately interested in the statistical performance of this decision X, of our like policy which route to take to travel to the University of Constance. And the question is, okay, what are the guarantees we can give? And how do this guarantee depend on the available data that we have? And now, here comes the third difficulty, and this is where now again the dynamical system comes into the game. So far, the first two bullet points apply to, I would say, a generic machine learning problem. Now, in reinforcement learning, the difficulty is also that the samples are generated from a dynamical system. So you don't have IID samples, all the beautiful statistical tools do not directly apply. So one has to somehow take the underlying dynamical system into the game. And this is what makes reinforcement learning so hard. Good. So here is another graphical visualization that can help. So in practice, what do we have? We have data collected from the past. Now with this data collected from the past, we want to take now, in present, right, an optimal decision X, and the subscript T means that depends on my training data set. And then of course, ultimately what we are interested in machine learning is the performance of this decision when applied in the future on new data, right? That is the kind of notion of a generalization. You're interested if you play this policy of travel time in the future, what would be the expected travel time to come to the University of Constance. Good. Now, okay, so what is the difficulty here? You need a mechanism that maps the data into a decision, very roughly speaking, that, okay, can be computationally expensive. And in the second, you want to derive the underlying statistical bounds. And they, of course, depend on what was the decision mechanism used in the first place. Now, I would like to give you a little bit an intuition why these are difficult problems and what one needs to be aware of. So the first one, I would say how to take the data and map it to a decision. That is a field that is relatively well studied. So this relates to this operations research that I mentioned in the beginning. That is one of the field of my interest, how to design optimization problems, how to design optimization problems that are also easy to solve or can be solved in polynomial time. And there is a very rich literature on robust optimization, dynamic programming, etc. that can be exploited here. Now the second one, about the statistical guarantees, I would like to walk you through, I think, a very insightful example that can show why, when working with training data, one has to be careful when kind of implementing the data in an optimization problem. And this will relate to what in statistics is known as overfitting. So one has to be careful that the underlying optimization solution is not too tightly put into the available data, right? You shouldn't trust the data too much because that will lead to overfitting when you later then generalize. And okay, so here is the example that I think everybody can understand. It is quite interesting. So imagine you're the manager, a project manager in a certain company, and your team submits 10 different projects to you, and you have the money to execute 5 out of the 10 projects. Yeah? And your goal is, of course, to maximize the so-called net present value. I mean, could think of kind of a kind of revenue or as a net present value. So now if you would know what are the future net present values of these 5 submitted project proposals, it would be easy, right? You would support project number 5 to 10 and you would generate the highest average net present value. Now, of course, and which would be something around 9, let's say, million euros. Now, of course, in practice, because these are just project proposal, you haven't executed the projects, you don't know the future net present value, you have to estimate it. So they will be uncertain, the true net present value of these projects. And now, for simplicity, assume that half of the projects you overestimate the net present values, half you underestimate the net present value. This, okay, at least is an unbiased estimate, and this could happen. Now, what would you do as a project manager? Now, your team submits these green and red numbers to you. Of course, you would reorder the projects according to increased number of estimated net present values, and now you would support project number 3, 10, 5, 7, 9. Huh? And then, okay, you would give the money to these team members, they would execute the project, and then what you would get in the end, okay, is the following here. So you would get this estimated mean net present value. That is what you would estimate, something around 9 or 9.5 million euros. And now here comes the disappointment surprise. Now the true realized net present value, of course, for the green one is lower because you overestimated, and for the red one is higher. So now you see in blue, this is now the true realized net present values. And of course you take the mean of that, and that is around 1 million euros smaller than what you kind of estimated. And of course this will have severe consequences for you as a project manager. So kind of 1 million euros short. And why did this happen? So this is kind of reminiscent of overfitting. Because you trusted your data too closely and just solved the optimization problem very tight to this data you had. Now, what is the key idea in my research is that how can we kind of safeguard optimization models and machine learning models that such overfitting phenomena cannot happen, that can provably not happen. And okay, here is one slide that is a little bit technical. The idea is not just to blindly minimize the expected loss using the training data, but adding a so-called regularization or a so-called kind of conservatism, which is this maximization here. So we are trying to find a decision that not only performs well on the unknown model P, but on a kind of worst case realization that lies in a so-called ambiguity set here, which is generated from my data. Yeah? And of course, you don't want this set to be too large, because otherwise you would end up with a very conservative solution. So there is a kind of tension there. But okay, the beautiful thing is that with these models, and okay, I'm not going to go into that, but one can actually quite carefully analyze how one would construct such an ambiguity set in a statistically smart way, such that you get such a generalization bound, which loosely speaking says such an overfitting phenomena will not occur with high confidence. And then, okay, hopefully also this optimization problem can be solved efficiently using a computer. Yeah? Okay, good. So now, let me come back to the building control problem. Just a very simple illustration of a reinforcement learning problem. So imagine that your state is the temperature difference from the nominal value. Let's say the nominal value is 22 degrees, and ST is the difference between the actual temperature and the 22 degrees. And you have n rooms, yeah, in the entire campus of the University of Constance. Now, AT, you say you have m radiators distributed around the campus, and AT means the energy provided into the rooms by the different radiators. And now we would, okay, go back to our physics course, recall the heat equation, which is okay, an SdPdE, but then okay, we would say, you know, locally a linear approximation is often good, so we would write down a linear dynamical system approximating the development of the temperature in the buildings, which would be this one. Now, A and B unfortunately are not known, because these are complicated matrices that depend on, you know, the materials in the room, how many people sit in the room, and I mean, this is complicated to model. So we would like to use a data-driven approach and not a physical modeling approach. And okay, WT is external noise. Now, for some reason that is known to us from the theory of Richard Bellman, we would like to find the heating policy AT, you know, the optimal input of the heating systems, as a linear so-called feedback policy from the state. Yeah? So, but of course the K is not known. The K we will optimize, this matrix K. Okay, and now which K would we like to find? We could say, okay, we want to find the K that drives our state close to zero. That means we go to the reference value of the temperature of the 22 degrees by using the least amount of energy. So this second term here is proportional to the energy fed into the heating system, and this is a penalty term if you're away from the reference temperature. And now the goal is to find the sequence A such that this combination here is minimized. Good. Now, unfortunately, so if A and B would be known, this is a classical instance of a so-called linear quadratic control problem. This has a closed form solution, and you could just open the book. This would be easy to implement. Now, unfortunately, A and B are not known, and therefore we need to apply a data-driven approach. So what we have is access to a temperature sequence. So we have the temperature at different days from the last year. And now, using this knowledge, we would like to figure out what is a good kind of heating policy. And how would we do that? We would derive the so-called closed loop system. That's the linear system when we replace U with K times S. And then we would see that this is nothing else than just an autoregressive model. And then using that, we would write down the optimal control problem as the following simplified reinforcement learning problem. And here now you see the exact difficulty compared to classical machine learning problems. The probability distribution here now is a function of my hyperparameter that I optimize over. This is a so-called decision-dependent distribution, and these problems are really, really hard. If there was no K here, this problem would be relatively simple to solve. Good. But, okay, this is a reinforcement learning problem, and okay, there is hope for this problem. And I would like to quote like one of the legends in the field, Dimitri Bertsekas from MIT. So he said, what is the current state of the art in reinforcement learning? So in reinforcement learning, there are no methods that are guaranteed to work for all or even most problems, but there are enough methods to try on a given challenging problem with a reasonable chance that one or more of them will be successful in the end. So that means the zoo of developed methods is so large that if you try hard enough, chances that you will find a method that works on this problem is very large. But okay, as persons interested in fundamental research, of course, this is not fully satisfying, right? Because we need to trial and error, and of course, it would be much nicer to know a priori which method should we work, which method should we use for this problem, and what is the probability that it would work. And this is what current research tries to do. And we have worked a little bit on that problem, and actually it turns out for this very simple problem, there is hope to solve this problem, like even theoretically with a given method. But, so here is the but, this of course is a very simple problem. We have a linear dynamics, we have a quadratic cost, and the works that have been developed for these problems heavily rely on both of these concepts. And if you go, for example, with a even slightly nonlinear system, a slightly more complicated cost, is totally open how to solve these problems, at least theoretically. Practically, as said by Berzegas, there is many methods that work well. Good. So now, we have seen started with the optimal control problem in quite a general setting, and seen that if the dynamics is unknown, this problem already is much, much more complicated than just classical dynamic programming. And you have phenomena like exploration versus exploitation dilemmas, which are totally present in classical dynamic programming. Of course, you have the same kind of computational headaches that dynamic programming has, like the curse of dimensionality, of course, is also present in reinforcement learning. And you have like many, many more problems of more statistical nature. Now, motivated by applications, one could even go a step further and say, how about if not only the dynamics is unknown, but also the cost is unknown? And this is then what brings us to so-called inverse reinforcement learning or inverse optimal control. Then, for example, a first step would be, how about if the dynamics is known, then people would call it inverse optimal control. And this is a field that is also now gaining trust over the last years with methods being developed. And I think this is a problem that is highly interesting also to model and understand human and animal behavior. So what is that? And this is, now I think almost to the end of my presentation. So let's assume we have this optimal control problem and the cost functions now are unknown. But what do we have? I mean, something we need to have. So we have an observed trajectory consisting of state and action at time t, where the action is played according to some policy we know, or we observe. And now the goal is, of inverse optimal control, to infer the cost, the running cost c and the terminal cost g, such that the played action sequence is optimal, right? And why is that? Because you assume that, for example, animals, they are designed such that their behavior is optimal with respect to some utility. They maximize some utility. The same is for agents in a kind of economic model. You assume that agents are rational and behaving optimally, but of course what you don't know is the corresponding utility function they're maximizing or the corresponding cost function they're minimizing. Now, yes, so this is one motivation for inverse optimal control or inverse reinforcement learning. There is another one more in the statistical learning theory, which is known as apprenticeship learning. So we'd like to understand statistically how could an individual learn a task from observing expert behavior. So that an individual would just study many, many different trajectories of an expert behavior, and with that try to generalize or learn how also to master this task. So this in robotics is very, very prominent task. And the last one, which I personally also find interesting and that gives a motivation for inverse optimal control, is to analyze the optimality gap of a policy when you have uncertainty in the cost. So think of that you are a retailer, a big online retailer, and you have derived over the years some good model that would help you to understand consumer behavior. And now imagine that something changes. So there is, for example, a pandemic or some kind of raw material prices increase, and now you would like to understand, is the behavior of my consumers that I assume to be optimal in their specific utility, do I need to expect that this will heavily, drastically change? Or could I expect that the behavior will only slightly change because it's still, even if some cost functions, parameters slightly change, is still almost optimal. And I don't need to prepare myself to a drastic change in consumer behavior. So this is this kind of suboptimality gap. Now, this is a problem that I've started just a few months ago to work on, and therefore it would be too much to say that I'm a deep expert on it. However, I think it's fair to say that there is a very rich literature developed in the last 5 to 10 years on these problems, with two kind of limitations that applies to, I would say, the vast majority of existing methods. So most of the existing methods are either designed for finite state and action spaces, which heavily kind of simplifies the underlying computation and statistics. And the second limiting assumption that is often done is that methods developed for inverse optimal control and inverse reinforcement learning rely on access to so-called Markov Decision Process solver. What is that? So these methods often assume that for a given estimate of C and G, you can solve this problem. You have an oracle that spits you out the optimal solution to that. And of course this is problematic because, as mentioned in the beginning, optimal control problems per se are difficult to solve. So assuming that you have access to such an oracle, this is a problematic assumption. Good. So now, and how about the finite state space? So if you would think of an inverse optimal control problem where you say you want to learn how to drive a Formula 1 car and you have access to video recordings of Lewis Hamilton and you observe like how this person drives. So you have data from expert behavior and now you would like to teach yourself how to optimally drive a Formula 1 car in the sense that you estimate the utility or cost function that Lewis Hamilton has in his head that allows him to drive so superior. Of course, like there you have a state space that is position and the velocity. That is not a finite set. Yeah? Of course, you can discretize and say, okay, I use that as an approximation, but this is a state space that inherently is like infinite. So therefore, okay, what we have started to look at, and that's also a little bit the motivation from the control people, so these people are interested in infinite state and action spaces. And we could show that this inverse reinforcement learning problem, so there is a modeling framework which is known as a linear programming characterization. So you can take this dynamical optimal control problem and lift it to a linear program, which is a static problem, but in a higher dimensional space. And then the problem is that this is not directly amenable to a numerical solver, so then you need to kind of develop approximation methods for these complicated problems. And you also need to work with the available data, use sample complexity bounds. Okay, this is too much for today's presentation. That would be a specified talk on inverse optimal control and inverse reinforcement learning. However, the punchline is that I think these methods are very, very powerful, general, and potentially interesting to analyze and explain human and animal behavior. Good. So with that, actually I come to the conclusion of my presentation. So I gave you a little bit an overview on some of my research interests, which I personally see it as a kind of fusion of three main topics. One is learning and classical machine learning. The other one is dynamical systems and how to steer, manipulate dynamical systems, which is sometimes known as optimal control. And the third bubble is more the algorithmic bubble, where we deal with the underlying optimization problems and how to solve them, how to analyze the solution quality of an optimization problem. And of course, like these three kind of themes are embedded in an interest on the algorithmic side, right? So in the end, our goal is to derive algorithms that scale well, such that they can hopefully be used for practical applications. However, also to derive theoretical understanding of this quite complicated and quite complex reinforcement learning type of problems. So if any of that is interesting to you, or if you just would like to have a coffee or a chat or anything, don't hesitate, please contact me. It would be a great pleasure to get in touch with more people from the collective behavior cluster. Yes, and with that, I would be happy to take any questions if there are.
Thank you so much, Tobias. Are there any questions here in the room? Yes, who was first?
Thank you very much. I'm just wondering how to really apply it to the everyday biological question. For instance, if you say dynamical system, you can assume that maybe it's nonlinear and has attractors. And I would wonder, in your approach or with your experience, would you suggest to look at an individual fish, a small group of fish, or should you start with a huge group of fish to understand and derive ideas about the system itself? Or would you need to sample all of these fish sizes because you assume that the size of the group might be an important parameter in the dynamical space?
This is a very interesting question, thanks a lot, and also a challenging one. I'm not sure whether I'm expert enough to answer that. I would like to say that the optimal control problems have been actually quite successfully applied to kind of, how is it called, you take like a group of fishes and you take a kind of mean field or population approach. So there is an entire branch of research on optimal control, how to analyze these population models, where you don't model individual fishes but entire populations, and you're trying to describe how can you steer the population of species to a certain target goal. So therefore, for sure, I think there is merit in using these tools on the population level. Now, on the individual level, of course, I think the individual level is easier, right? The individual level, I guess you could model like that. With that, I'm not so sure how interesting it is to describe an individual, let's say, fish and see how this behaves. So probably, yeah, I think both problems, in my opinion, can be phrased as an optimal control problem. In my opinion, depends on what is your goal, which type of insights you would like to get. And the non-linearity, okay, here I guess I have to lower a little bit expectations. I think the non-linear problems in optimal control or reinforcement learning are extremely hard. So I think there is very little theory that can be developed for optimal control problems where we have an underlying nonlinear dynamical system, which doesn't mean that you cannot use the underlying algorithms, and which doesn't mean that the underlying reinforcement learning algorithm do not have a chance to perform very well. But I think you probably will lose the statistical and mathematical guarantees. Or you need to re-derive those, which will be a seminal piece of work.
Yeah, also from my side, thanks a lot for this interesting talk. I've heard that another problem of reinforcement learning is that it's somehow it's somehow limited to like the length of the kind of sequences it can work on. Now, would you think that is also a big problem of when you study the behavior of animals? I mean, I know that this is a problem in robotics where like the sequence of actions that can be learned is easily then reached, but maybe for like animals and even for humans, I would suspect that we don't even have very long sequences that we execute to find a decision or so. Yeah, that maybe most of our decisions are intuitively but based on very short ranges. Yeah, is that
yes.
true?
I think this makes total sense to me. So these big successes I've shown in the beginning of AlphaGo and Google DeepMind, so these methods are highly data inefficient. So they rely on extremely enormous access to data. Yeah? And if you want to now work with real, let's say, with limited amount of data that you collect, for example, on your fantastic hunger for the animal behavior, this probably is by magnitudes too little data to make these methods work. Yeah? So this is also what I wanted to say in the beginning, actually. So these methods so far show this amazing performance for mainly computer games where you can simulate and generate as much data as you want. And with the real world applications, for example, to explain human behavior, I fully agree that in the long term, to make kind of reliable predictions, you would probably need so many trajectories of data that this is just totally unrealistic to ever have. Yeah? And therefore, I think one idea that, because the number of data points you need usually also scales with the horizon of the problem you want to solve. So therefore, I fully agree. I think one probably should start with a very short-term prediction or short-term explanation of a behavior one would want to do, because with a limited amount of data, there is some hope to say something there. But of course, if you want to predict the behavior of a fish in 3 hours from now, I guess this is hopeless. Nobody can do that, yes. Yes, and then you might also have this very non-linear behavior, which makes it even more hard. Yeah.
I was really interested in the point of having an idea, a better idea when overfitting happens. So is it possible with your methods to give an indicator that we reach a certain threshold or boundary of overfitting? Can you predict overfitting well, or is it you can only later infer if you were able to see overfitting? So,
okay, yes, so this is also a good question, thanks. So in principle, I mean, I'm not sure whether one can predict that overfitting for sure happens, but one can, I mean, if you have such a generalization bound that I showed you, so there exist methods where you can prove that overfitting will never occur. So you have a certificate or a mathematical proof that tells you, like, no matter how unlucky I am, overfitting is not going to occur. Which, okay, then is also a probabilistic one, but okay, this is one thing. So, and the other methods, for example, the one that I showed you, like I reverse engineered that. So I engineered that to show you the overfitting. Now, we could, with that example, for example, we could see, like, if situation hadn't been that extreme where we underestimate and overestimate, it's quite likely that overfitting would be mild. Yeah? But nevertheless, I mean, these things, something like this could happen, right? Maybe not in that extreme level, but for this model, like, the overfitting will occur. The intensity of the overfitting, I think that is hard to predict, because that depends on the realization of your uncertain parameters. And now to your question, so in practice, how do machine learning people combat the overfitting? They add regularization. So they add some kind of regularization parameter, L2, or the Tikhonov regularization, many different regularizers that are added. Now, these regularization parameters, usually you have to scale with a certain factor, the regularization term. And of course, the higher that factor, or the higher the regularization parameter, the more it combats the overfitting, but the more you change your problem, because your problem you wanted to solve is actually without the regularization term. So therefore, and this is a kind of, usually machine learning people use that as a tuning parameter. So you want the smallest value for this regularization parameter that prevents overfitting, but that doesn't change your problem too much. And how to select this parameter a priori, I think that is a holy grail. So I think in general this is impossible. People use kind of statistical tools, how to later tune. So they use cross-validation techniques and tricks how to fit this parameter, but it's a tuning parameter. And of course, I think that would be a very, very major result, yeah, if something like this could be shown.
Any more questions? Thank you so much, Tobias, for
thank you for having me here.
Today. Yeah, thank you. And yeah, I'm happy to let you know, although the room is rather empty, we had like 57 more people on the online with us. So there's high interest in your research, and we're very happy to have you here today. Thank you.
Thank you so much.